Hello, how are you? Thank you so much for being here on our Thursday lecture. Today, we're going to start off with some review content, and then we'll go on to a new chapter, chapter 6, and section 6.1. So I'll begin with the review correct material, and I'll go into chapter 6.1. And then at the end, I'll answer any of the homework questions you might have. So just in case you don't have any homework questions, you can log off without having to wait on everyone else. All right, so I'll go ahead and share my screen and start with the review portion and the announcement I told you what we're going to review today. So mute all of you, just so we don't hear your background noise, and I'm going to share my screen. All right, so today we're starting with some review stuff. So we're gonna go over factoring, particularly factoring a trinomial. So we're gonna start off with the file called the factor game. Now this one is just getting you used to the idea of the pairings that you're looking for when factoring. So let's start off with this correct 136 material. And I didn't email you this one. I put it on today's announcement. I think I forgot to include the factor game into the email, but it is in today's announcement. All right, let's start the factor game. Factoring trinomials, the preparation, part 1. The factor game is a numbers game with these rules. You are given two numbers, a product and the sum. Product means multiplication, sum means addition. You must find a factor pair of the product number that adds to the sum of number. The correct factor pair is called the winning combination. Special notes. In a single factor game, it is possible there is no winning combination, no factor pair that works. And if there is a winning combination, there will only be one winning combination. And it does not matter the order the numbers of the winning combination are written. Let's do an example. Example 1. Find the winning combination for the given product and some numbers. So I want to think of two numbers. When I multiply them, give me 18. And I want those same numbers when I add them to give me 9. So you're thinking of all the numbers that give you 18, 1 times 18, 2 times 9, 6 times 3. You think, oh, 6 times 3 works, right? 6 times 3 gives me 8, but also 6 plus 3 gives me 9. Cool. All right, let's do part B. You want to think of two numbers that multiply to give you 36, and you want those same numbers to add to give you 20. So you're thinking of all the ways you can get 36. So you get 36 from 1 times 36, 6 times 6. It can be divided by 2, so 2 times 18, by 3, 3 times 12, 4, 9 times 4. So all these numbers. So which one works to where when you add them, you get 20. 2 times 18 works, and 2 plus 18 gives me 20. And you have your work here. So we did A, and for A that we did here, has the work for it. And it's showing you how 1 times 18 gives you 9, 2 times 9 gives you 18, and 3 times 6 gives you 18. But when you add them up, there's only one that works. We wanted it to add up to 9, so that's the winner. For B, that we just did, we have it there, our work, and we see how 2 plus 18 is our winning pair. Lastly, for C, what numbers can I multiply to get 40? When I add those same numbers, get 15. And for 40, we can use 1 times 40, 2 times 20, 4 times 10, and 5 times 8. But we want the sum to be 15. Which one adds to give us 15? None of them work, right? There is no winning combination. And that's okay. That sometimes happens. So let's go ahead and do this group exercise. We want to think of two numbers that when we multiply them, give us a number below. So what two numbers can I multiply to make 20, but when I add them, get 12? So 10 times 2 gives me 20, and 10 plus 2 gives me 12. Checks out. Cool. What two numbers can I multiply to get 30, but when I add those same two numbers, I get 12? 3 times 10. I have to make a list. This one's not coming to me so quick. 3 times 10 give me 30. 15 times 2. 1 and 30. Is that it? 5 and 6. And that's it, right? And when I add them, I get 13, 17, 31, 11. None of them add up to be 2. So this one does not have a winning pair. Lastly, 36. I can get 36 from 1 times 36, 2 times 2 times 18, 3 times 12, 4 times 9, and 6 times 6. So which one of these add up to give me 15? 3 and 12 does, right? So 3 plus 12 is our winning combination. Now, sometimes they're pretty easy to notice. Like I think this one was pretty easy to think of. 30, I couldn't think of a pair that would work. When you're unsure, you can make a list, and that's okay. If the product number is positive and the sum number is negative, then the factors in the winning combination will both be negative. So here we have an example. So we want to think of two numbers to when I multiply them, I get positive 18, and when I add them, I get negative 11. All right, if that's the case, keep in mind that a positive times a positive gives you a positive. A negative times a negative gives you a positive. And a negative times a positive gives you a negative. And a positive times a negative gives you a negative. So that's what it's saying. If your product is positive and your sum is negative, then your two numbers that you think of have to be negative in order to make your product positive, because we want this to be positive, and that's super important. So what two negative numbers can I think of to where when I multiply them, I get positive 18, but when I add them, I get negative 11? All right, so we can get 18 from 9 times 2. That would work, right? Sorry, negative 9 and negative 2. When I add them, negative 9 and negative 2, I get negative 11. So that works out. Let me emphasize that negative. And we have our work below. So for B, the product of 36 and the sum is negative 12. So I think of two numbers to when I multiply them, I get positive 16, but when I add them, I get negative 12. So what numbers work? We have right here, right? Negative 6 and negative 6. Because negative 6 times negative 6, it gives me negative 30. I'm sorry, positive 36. So when I add them, I get 12. All right, let's go to example 3. If the product number is negative, the factors in the winning combination will be opposite sign. So again, it goes to if I'm multiplying and I want a negative, right? We see this negative right here. I can only get a negative by a negative times a positive or positive times a negative. Regardless, they have to be different signs. All right, and it also tells you here highlighted. The larger value will have the same sign as the sum number. So whatever happens, I need to make sure that my bigger number is positive and my smaller number is negative, because when I add them, I want to make sure it's positive 5. But they'll come to play as you're working through them. So what numbers can I multiply to get negative 24? And we have our work right here. We have negative 1 times 24, negative 2 times 12, negative 3 times 8, and negative 4 times 6. And we see we have the winner right here. 3 times 8 gives me 24, but I need to make sure that 3 is negative. So when I add them, I get 5. So we have negative 3 and positive 8. So if I add 8 and negative 3, I get 5. Same thing for B. I see that my sum is negative, so I have to make sure my bigger number is negative as well. But if this is something to keep that's too weird to keep track of, you can just think just as before. What two numbers can I multiply to be 36? But when I add them, I get positive 5. And if you're ever unsure, you can make a list, just like we have right here. 1 times 36, 2 times negative 18, 3 times negative 12, and 4 times negative 9. And we see that 4 times negative 9 gives me 36. And you make that 9 negative so that I have a 5, a negative 5. So 4 and negative 9. All right, now we have some focus exercises. Let's do 1 and 5. All right, so I want to think of two numbers. So when I multiply them, I get 18, but when I add them, I get 11. So 1 times 18, 2 times 9, 3 times 6. Write them down. 1 times 18, 3 times 6, 2 times 9. 2 and 9 works, right? Because when I add them, I get 11. So 2 times 9. And when I add them, 2 and 9, I get 11. Cool. 5. The product of 25 that add up to negative 10. Okay, so I can get 25. Let's make a quick list. I can get 25 from 1 times 25, 5 times 5. That's it. That's the only way I can get 5. I'm sorry, 25. I want positive 25, but I want it to add up to negative 10. All right. If I make them both negative to make positive 5, that'll work, right? So negative 5 times negative 5 gives me 25. And negative 5 plus negative 5 gives me negative 10. Cool, we found our winning pair, negative 5 and negative 5. Now the purpose of this little correct review is just to get you ready for factoring. So let's go on to the next slide. Not the next slide, the next review one. So we have factor trinomial. So I wanted to go over that today. So new file that I sent you today. Factoring is pretty much trying to come up with the same binomial or whatever. Usually it's a binomial, but it doesn't have to be a binomial. I want to come up with the two things I want to multiply them, give me a trinomial. All right, let's begin. Factoring quadratics. A quadratic polynomial is in the form of ax squared plus bx plus c, for which a cannot equal 0. However, b or c may be 0. If b or c is 0, then the quadratic has fewer than 3 terms. For example, these are all quadratic polynomials. And in general, for it to be quadratic, I need to have an exponent of 2. your highest exponent be 2? Your highest exponent is your degree of your polynomial. A quadratic means our highest exponent is 2. It's a degree 2 polynomial. So here we have some example of quadratics. So here we have 1, 2, 3 terms. Here we only have 2 terms, and here we also have 2 terms. But we notice that for all of them, we have that square, that term squared, and that makes it quadratic. Group exercise 1. Which of the following is a quadratic polynomial? Why or why not? So as we take a look at the first one, my highest degree, is it 2? No, right? So this one is not a quadratic. My highest degree is actually degree 1. So this also is not a quadratic. We finally see one with the exponent of 2. That one is a quadratic. And here we have an exponent of 2. You can say yes. Your reasoning? Well, by definition, it doesn't really directly say, hey, you need to have an exponent of 2. That's kind of your layman's terms. But notice that your leading coefficient, a cannot be 0, and a is only the term squared. It does continue to say that b or c can be 0, meaning we don't need to have an x term or a constant term, a term without a variable. But we do need to have that x squared. So just like we do here and we do here. That's that necessary term for it to be a quadratic. Moving forward, some quadratic trinomials can be factored into a product of 2 binomials. For example, each one of these is factored as shown below. We can verify the factoring is correct by multiplying the binomials using the FOIL method or other technique. So here it's just telling you that this is what we're starting off with. That's what we're starting off with. And then it tells you that it factors into this. But then it goes on to say that you can verify your work by multiplying it out, or FOIL. And you see that what you end up with is exactly what you got in the beginning, right? That's factoring. This step right here is what we want. And to get that highlighted part in blue, we need to factor. Now, why do we want to factor? We want to factor because what's in blue, this is now linear. Meaning that I can solve a linear equation. We can set each one equal to 0, and we can solve for x. So we can have 2x plus 3 equal to 0 and solve. We can have x plus 2 equal to 0 and solve. This is an important feature in part of solving a quadratic, but there's other ways. Now, B and C explain the same thing over again, meaning you start off with your equation, and we can factor to get these 2 binomials. And if you multiply it out, you see that you get the same thing in return. So you are in no ways changing the value of it. We're just rewriting it. In our case, we're purposely going to rewrite it to have 2 linear expressions. Same thing for C. We start off with this, we factor it so we can now get these 2 terms. But notice we're not changing the value of it, because if we multiply it out, which we're just making go in circles, there's no need to multiply it out. We get back to what we started off with. All right, Each of these trinomials matches the trinomial we started off with, so we have verified the factoring is correct. I'm going to go ahead and skip exercise 2 and move forward. The question is, how do you get those binomial factors? Do we just guess? No, there is a process, and the more you see it, the better you'll become at factoring trinomials. First, factoring is the reverse process of multiplication. So we can think about reversing the steps of multiplying binomials, FOIL, and simplify trinomials, and apply to factoring trinomials. For example, let's multiply 3x plus 2 times x minus 6. We can start by finding the 4 FOIL products. So that means multiply 3x times x, we get x squared. 3x times negative 6, we get negative 18. 2 times x, 2x. And 2 times negative 6, negative 12. The middle two terms are like terms, and we can combine, giving us a trinomial. What it's saying is those terms in the middle, we can add them, right? They're like terms. So negative 18 plus 2, we get negative 16. So this means, 1, that 3x plus 2 times x minus 6 multiplies to be 3x minus 16 minus 12. And 2, 3x squared minus 16x minus 2 factors into 3x plus 2 times x minus 6. The reverse of this includes the following steps. Starting with a trinomial 3x squared minus 16x minus 12, write the middle term as two like terms. This will create a 4-term polynomial, which we can factor using grouping. So start with a trinomial. We have 3x squared minus 16x minus 12. Split the two terms and write the trinomial with 4 terms. So split the 16 into negative 18 minus 2. Now, how do you find those two numbers? We're going to use our factor game. We have to multiply, so each term has a name, A, B, and C. Your A always is attached to the square, your B is attached to the x, and your C is your constant. So you do your factor game. You have to multiply A and C, A times C, and you want the sum of it to be your B. So what two numbers can I multiply to get A and C such that those same two numbers add up to give you B? Okay, well, A times C is 3 times 12. 3 and 12. 3 times 12 is 36. So what two numbers can I add to get 36? Maybe write it so I don't just have letters. So what two numbers can I think of to multiply to give me 36, but add to give me negative 16? Well, we saw a combination before, right? 2 and 18 give me 36. Oh, that's a negative right there. So 3 times negative 12, that should have been negative 36. 2 and 18 give me 36, but if I add them with 2 and negative 18, I get negative 16, just like I wanted, right? That should be negative. And that's how we get these two numbers here. This is from our number game. That whole slide we spent like 20 minutes doing, it's coming into play here. So that's how we get that to negative 18 and that 2. Notice if we add them, we move back up to negative 16. But we purposely wanted to create 4 terms. Now you want to group your first 2 terms and your last 2 terms. You want to group them and think, what's the GCF? What's the greatest common factor I can factor out? So for my first one, it's a 3x. I can factor out a 3x. For my last two, I can factor out a 2. So if I go ahead and factor that 3x for my first term, so I divide each one by 3x. Think of it that way. Divided by 3x, divided by 3x. 3x squared divided by 3x, we're just left with x. 18x divided by 3x, we get 6. Don't forget your negative. For our last two, we can divide out a 2. 2x divided by 2 gives me x. 12 divided by 2, we get negative 6. Notice you have the same thing in your parentheses. You have x minus 6. And x minus 6, that's one of our factors. And the last two are made up from our terms, the 3x and the 2, 3x plus 2. This is factoring a trinomial. The most important question is, in all this is, how do we know what two like terms to write in place of the middle term? In other words, how do we know to break up negative 16x into negative 18x and 2x? The answer to this question is the factor game, which we already did. Trinomials and the factor game. Now let's put the factor game to good use. Consider a trinomial of the form 2x squared plus bx plus c, where a, b, and c are integers, and a can't be 0. Again, a can't be 0 because we need to make sure that the square, x squared, is still there. In a trinomial, ax squared plus bx plus c, the product is ac and the sum is b. Given the trinomial, identify the product and sum numbers. Find the winning combination of the factor game, if there is one. Okay, so let's go ahead and do this. So I need to multiply 3 and 8. 3 times 8 gives me 24. And our middle term is going to be negative 14. So usually the way I was taught is you do a little x, right? So what two numbers multiply to give you 24, but add to give you negative 14? And we think of what we get. 3 times 4, 2 times 12, what works? So 2 times 12 will work, right? 2 and 12. Now I need to make sure they add to be negative 14. Make them both negative, and that still matches my positive above. So for B, same deal. 5 times 12, that gives you 5 times negative 12, we get negative 60. And our middle term is negative 4. So what two numbers can I multiply together to get negative 60, but add to give us 4? And you can think of your numbers. 1 times 6, 2 times 30, 6 times 10. Oh, 6 and 10 have a difference of 4. That would work. So 6 and 10. All right, I need to make one of a negative to get negative 4. So negative 10. 6 plus negative 10 gives me negative 4. And 6 times negative 10 gives me negative 60. Cool, we check off. 3 times negative 8. That gives you negative 24. All right, what two numbers multiply you negative 24? That to give you 6. So I have 2 times 12, no, 3 times 8, 3 plus 8, that gives you not 6. 3 minus 8 does not give you 6 either. 7 and 4, no. Okay, so we can't, not even that 7 and 4 will work. 6 and 4, no. So there aren't any numbers that work. So there's no combo. We wouldn't be able to factor it. Not factorable. There's no combination. Our combination are these winning numbers, right? Negative 2 and negative 12, 6 and negative 10. All right, let's do exercise 3. All of this is to set you up for success in factoring. If you're a factoring pro, then this should feel pretty easy. If you're not a factoring pro, make sure you finish the remainder of this review. Given the trinomial, identify the product and some numbers. Find the winning combination for the factor game if there is one. All right, so what's our product? Our product comes from 4 times 5. 4 times 5 is 20. Our sum, we want a 12. So we want to think of two numbers when I multiply them to get 20, but when I add them to get 12. 2 and 10, right? 2 and 10. 2 times 10 give me 20. 2 plus, or times, and 2 plus 10 gives me 12. Cool, that works out. Our combination is 2 and 10. Any questions about the product? The product game is called? No? All right. So let's continue with B. 5 times 6 give me 30. My middle term is negative 13. So I always have to draw that little x. What numbers multiply to give me 30, but add to give me negative 13? Well, negative 3 and negative 10 do the job. And always check it out before you're sure. Negative 3 times negative 10 gives me positive 30, and negative 3 plus negative 10 give me negative 13. Great. So negative 3 and negative 10 are a winning combo. Let's take a look at 6. 6 times negative 4, I get negative 24, and my sum is negative 13. So what numbers can I multiply to get negative 24 and add to give me negative 13? All right, so 3 and 8? No. 6 times 4? No. 2 and 12? No. I don't think there's a winning combination, right? All right, so there's no winning combination. This will actually be not factorable. Let's do 3 times negative 4 gives me negative 12, and my middle number is 4. So what numbers multiply give me 12, but add to give me negative 12, but add to give me 4? So I can get 12 from 3 times 4, 6 and 2. 6 and 2 would do the job. 6 and 2, and I want to make sure my 2 is negative, because 6 plus negative 2 give me 4, and 6 times negative 2 give me negative 12. So 6 and negative 2 would work. All right, this group exercise 3 is just to think of the two numbers that would work to give you your middle term. All right, factoring trinomials using the factor game. The whole point of the factor game is to be able to rewrite a trinomial into four terms. It is the winning combination of the factor game that tells us how to split the trinomial's middle term into two terms, thereby making it a four-term trinomial. Consider factoring the trinomial 8x squared plus 10x minus 3. There are steps to factoring a trinomial using a factor game and factoring by grouping. 1. Identify the product and some numbers and find the combination of the factor game. So in this case, 8 times negative 3, we get negative 24, and my middle term is 10. So what numbers work so that when I multiply them, I get negative 24, and I add them, I get 10. 12 and negative 2 work, right? 12 times negative 2 gives me negative 24, and 12 plus negative 2 gives me 10. The two factors in the combination are the coefficients of the next x terms to make the trinomial into a four-term trinomial. In other words, the middle term plus 10x can be replaced by 12x minus 2x. That's the whole purpose of doing this. Once we create a four-term trinomial, there's four terms, I group the first two and the last two. So group your first two and your last two. Now you want to factor the greatest common factor between each two. So because your first pair have that x squared and that x, you're always going to factor for sure an x, but also in your terms, what's the biggest number that divides 8 and 12? That'd be 4, right? So we're going to factor a 4x. On my last two, I want to be able to factor a negative, and that's about it. So it'd be a -1. Your goal, your unwritten goal is you want to have the same thing in the parentheses. See how that is written in bold? You want to be able to have the same thing in the parentheses, so that we can factor that 2x plus 3 and write it as 2x plus 3 times 4x minus 1. And if you're ever unsure, you can always verify your factoring by multiplying the binomials together. You should get back what you started off with, and that's a way of checking your work. All right, so let's go ahead and do some examples. Let's do group exercise 4. Factor each trinomial using the factor game, and write it as a 4-term polynomial. Then use factoring by grouping. If the factoring cannot be factored, write prime. All right, let's start off with A. What two numbers can I multiply? Well, I multiply 3 and 6, I get positive 18. My middle term is 11. So I want to think, what two numbers can I multiply to get 18? But when I add them, I get 11. 9 and 2? 9 times 2. All right, so we're going to replace 11y with 9y plus 2y. So that we now have 3y squared plus 9y plus 2y plus 6. Okay, now I want to group my first two and your last two. If I take a look at my first two, I can factor out a 3y. If I factor out 3y, I'm left with y plus 2. Looking at my last two, I can factor out a 2. If I factor out a 2, I'm left with y plus 3. Notice we don't have the same thing in the parentheses. So that means we made a mistake. So that should have been a 3 for that first one. Because 9 divided by 3 gives me 3. That makes sense. All right, so let's go ahead and rewrite it. 3y and a 2, positive 2, so we write 3y plus 2. And in parentheses, we have y plus 3. We have now factored. All right, let's go ahead and do B. So I want to multiply my first and my last. That gives me 8. And my middle number is -5. So what two numbers can I work with? So when I multiply them, I get 8. But when I add them, I get -5. All right, so 2 times 8, that wouldn't work out. 1 times 8, that wouldn't work out. There's no such numbers that would work. So we can write prime. Now, they didn't emphasize it when you have a leading coefficient of 1. If we don't have a leading coefficient of, if you have a leading coefficient of 1, it makes things much, much easier. So you don't have to do as much work. So 1 times -30, you get -30. My middle term is a 1. All right, so what numbers multiply give you -30 and add to give you 1? 3 and 10, 2 and 15. 5 and 6, 5 and 6. 5 times 6 have a difference of 1. I want a positive 1, so let's make that 5 negative. -5 times +6 give me -30, and I add to give them to get 1. All right. Only when your leading coefficient is 1, your answers are, it's pretty much done. So your answer for this is M, minus 5, and m plus 6. You can go through the same thought process as we did above, but you'll get the same answer. And that's only when your leading coefficient is 1. You just take your terms and your variable. All right, let's go ahead and do D. 6 times negative 2 gives you negative 12. And my middle term is negative 1. So what numbers multiply give you negative 12 that have a difference of 1? 4 and 3. You want a negative 1, so you want to make that 4 negative. Negative 4 times 3 gives you negative 12, and negative 4 plus 3 gives you negative 1. So we can write this to be 6p squared minus 4p plus 3p minus 2. Let's group our first two and our last two. In our first two, we can factor a p, and the biggest number divides into 6 and 4 is 2, so 2p. And we're left with 3p minus 2. And our last two, there isn't a bigger number that we can divide into both of them. And our sign is where it should be. I have a minus in the middle, like we have right here. So let's just write a placeholder. So a plus 1, 3p minus 2. Now that we see we have the same thing in the parentheses, right? Let's factor it. 3p minus 2 times 2p plus 1. That's our answer. Okay, so that's all for factoring. If you need help with factoring, make sure to ask me for help, or you can go to tutoring. They have online tutoring. But make sure you practice these problems. Factoring is a key important feature for chapter 6. All right, let's go ahead and move on to chapter 6. Let's begin with 6.1. So 6.1 talks about solving trigonometric equations. So there's a note that wants us to review the factoring trinomials and solving quadratic equations. It's recommended for chapter 6. All right, so we did that first one, factoring trinomials. We did that one. On Tuesday, we'll do quadratic equations. We'll do that one on Tuesday. It's helpful for solving quadratics. Let's read your book. As you know, an equation is one expression equals another expression. Some of these equations are identities, such as t plus a equals a plus t, and cosine squared t plus sine squared t equals 1. These identity equations are true for every value of t, and no solving is necessary. Other equations, such as t plus 7 equals 1 plus 4t, and cosine t plus 1 equals 0, are true for only specific values of t. Our task in chapter 6 is to solve equations that are not identities. In this chapter, the trigonometric functions in each equation are not inverse functions, so they do not have a natural restriction. In chapter 3, we solve simple equations with certain limitations. Here are a few examples of chapter 3. So we have an in-class example. Find the value of x or theta with the given restriction that makes the equation true. So we want to find where sine is radical 3 over 2, and we have a restriction that it must be in quadrant 2. I think this is the last thing we did together, these type of problems. So looking only in quadrant 2, what is sine radical 3 over 2? So make sure you have your unit circle out, have it handy. And see sine is radical 3 over 2 at 120 degrees. Right here, right? We have the coordinate point of negative 1/2 and radical 3 over 2. and that's at 120 degrees. So our answer for theta is 120 degrees. Let's do B. We want to see where cosine is -1/2 in quadrant 3. Quadrant 3 is right here. When is cosine -1/2? We see that we have a coordinate point right here. Ooh. That gives us -1/2 and negative radical 3/2. And sine is your x. I'm sorry, cosine is your x. And that point is 240. So theta is equal to 240. Let's do cosecant. Cosecant, let's see. Cosecant theta is -2 in quadrant 3. All right, quadrant 3 is right here. And cosecant is 2 at 30 degrees. We have 30 degrees right here. So that would be 210 degrees. And you make sure it's negative. All students take, only tangent is positive, so cosecant would be negative. So our answer theta is 210 degrees. All right, let's go ahead and skip to example F. We want to see where tangent is -x, working only with quadrants. Pi/2, which is up here, all the way to 3pi/2. So I only want to work with these quadrants. Okay, well, when we want to get an answer of -1, recall your little tool to help you work through positives and negatives. We have all students take calculus. So really the only quadrant that would work is this one, because the other one would not produce a -1 for tangent. Now, if you look at your chart, we see that tangent is tangent is 1 at 45 degrees. So it'd be that middle tick mark. So that'd be 135 degrees, but they gave us radians, so we want to give them an answer of 3pi/4. So x is equal to 3pi/4. Now, why are we doing this? We're recalling what it means to have an argument, a limitation as to what your answer can be. And last time we saw something like this was in chapter 3. They're telling us our argument. It's telling us that theta can only be in quadrant 2, or in B in quadrant 3, or F between pi/2 and 3pi/2. That's type of limitation. That's something we'll see in chapter 6 as we try to find our answer. Note, in this textbook, if the argument contains a theta, the solution is written in degrees. If the argument contains x, the solution is to be written in radians. Let's expand the restriction to include more values of x and theta. Find intervals for x and theta. The intervals for x and theta are called solving intervals. A typical solving interval is 1 revolution around the unit circle. For theta, the typical interval includes 0, but not 360. So we write it in interval notation. I'm sorry, inequality notation, is that what it would be called? So it's telling us to go from 0 to 360. But notice how that 360 does not have a equal to. You don't have an equal to for 360. Same thing for radians. For x, the typical solving interval includes 0, but does not include 2pi. So we write it this way, from 0 to pi, but we don't write it equal to on the inequality for 2pi. All right, let's do in-class example 2. For each, use the following interval, 0 to 360 to find the values of theta that make the equation true. All right, let's do B and A and B. So we want to work with the entire unit circle, and we want to find where sine is negative square root 2 over 2. Well, keep in mind, all students take calculus. So that means sine is positive in the first two quadrants. So our only possible quadrants that will work are quadrants 3 and 4. And you see that sine is only negative at a negative radical 2 over 2 at 225 degrees and at 315 degrees. So theta is equal to 225 degrees and 315 degrees. Cotangent. For cotangent, we want to find negative radical 3. Again, think all students take calculus. We want a negative. When is it ever negative? Well, it's positive in the first and third. So the ones we want to work with are the second and fourth. So let's highlight those. Second and fourth. All right, cotangent is radical 3 at 30 degrees. So we're at 30 degrees from the unit circle, from our line right here. That's 30 degrees. And that would be 150 degrees. And this would be 30 degrees, right? And that would be 330 degrees. So cotangent theta is equal to negative radical 3 at 150 degrees and 330. Okay, let's go ahead and move forward. In class example 4, let's read that text above. We can find even more solutions by increasing the solving interval requiring more than one revolution around the unit circle. In each of the two examples, the solving interval requires 2 full revolutions around the unit circle. In class example 4, find the values for which 0 is less than or equal to theta less than 720 that make the equation true. So I want to work with 2 revolutions around the unit circle, right? But I only need to work with one of them, and then from there add to 360 or add to pi, depending if we're working in radians or degrees. So let's do example A and example 5 and A and example 4. So for A, cotangent theta of -1. Well, if we want a negative, we know all students take calculus. Cotangent is negative. Well, first of all, tangent and cotangent are positive in quadrants 1 and 3. If we want a negative, we want to work with quadrants 2 and 4. And cotangent is 1 at 45 degrees, so it'll be -1 at the 45-degree tick mark, which is that middle tick mark. So that's the measurement of 135 and 315. So we found the first revolution around. Theta is 135 and 315. But I want to work within 2 revolutions, but we still have that same value second time around as well. So we just add 360 to our answer. So we think 135 plus 360, we can use our calculator if we want. 135 plus 360, we get 495. So our answer is also 495. And 315 plus 360, we get 675. So all of these units together, all these measurements together make up our answer because we want 2 revolutions around your unit circle. We just add 360 to find the next one. And that gets you to your next one right there. Same thing for in class example 5. We see that we want to work with, well, we know one trip around the circle is 2 pi. Another trip around the circle will be another 2 pi. So that's also 2 revolutions. All right, let's go ahead and do A. When is sine 0? Well, sine is 0 at 0 and at pi. So x is 0 and pi. And we go ahead and add 2 pi to our answer. So we also want 2 pi and 3 pi. Remember, we're just adding 2 pi, a whole another trip around our unit circle. 0 plus 2 pi is 2 pi. 1 pi plus 2 pi is 3 pi. That's our answer. Equations with no restrictions. If we remove all the restrictions and eliminate the solving interval, so what we were talking about above is what we'll see to be a solving interval. Then there's no limit on the number of turns around the unit circle we can go looking for solutions. In other words, there are an infinite number of solutions. For example, a simple equation sine theta equals 1 has one solution, the first revolution at theta equals 90. For the second revolution, we add 360, we get 450. For the third revolution, we add 360, we get 810, and so on, as shown in the diagram on the right. We also consider the possible negative values of theta, such as negative 270 and negative 630, by repeatedly subtracting 360. So if we want to solve sine theta equals negative 1, which happens here, a unit circle is not limited to only one revolution. So we can just keep adding 360 and we will never finish writing all the answers, right? So there's a trick so that we don't have to spend our whole lifetime answering one problem. We represent all degree solutions by writing theta equals 90, and we add this little tidbit right there, plus 360k, where k is any and every integer, including 0 and negative integers. We abbreviate k as any integer by writing k is contained in z. Z is a set of all integers. So our final answer, we will write like this. Theta is equal to 90 plus 360, where 360k, where k is contained in z. And yes, you do have to write all of that. If you don't write all of that, you won't get full credit. So you have to remember this part that's, that 360k, comma, k contained in z. In a sense, this formula that helps us generate as many solutions as we want. We can set up a table of values k to show several solutions for theta. So here it shows us if k is 0, we get 90. If k is 2, if k is 1, we get 450. If k is 2, we get 810. So we see how k would hold true no matter what we plug in for k. It'll give us every measurement like we have here, 90, 45, 450, 810. And same thing if we go towards a negative. We plug in a negative value, we'll get those negative numbers. So adding k containing z will produce every point along the unit circle where sine is equal to 0. Likewise, the simple equation sine x equals 1/2 has 2 radiant solutions for the first revolution around the unit circle. We have x equals pi over 6, and x equals 5 pi over 6. For the second revolution, we add 2 pi to each term separately. For the third revolution, we add 2 pi and so on. We consider the possible negative radian solutions by repeatedly subtracting 2 pi. So instead of worrying about adding and subtracting, we just write it this way. We see how we still have that pi over 6 and 5 pi over 6. We have that written, but we're adding that other extra part, plus 2 pi k plus 2 pi k contained in z. Let's do in class example 6. For each, find all degree values of theta that make the equation true. Okay, so let's do A. It's kind of done for us. We see that secant theta is -2 at 135 and 225. So we have those answers written, 135 and 225, and we're going to add a plus 360k, where k is in z. Now we're adding the degree measurement because we have a theta. If we were to have an x, we would use radian. Okay, let's go ahead and do B. So when is sine negative square root of 3 over 2? Sine is negative square root of 3 over 2 in quadrants 3 and 4. And so theta is equal to 240 and also 300. But because we want all of the answers that could ever exist in the world, we have to add this extra part. Plus 360k plus 360k, where k is contained in your z. And z means all integers, so all whole numbers from the negative, positive, and 0. In class example 7, for each find all radian values of x, so all radian, that make the equation true. So we have A done. When is cosecant equal to 1? Cosecant x is equal to 1 at pi over 2. So that's our answer, x equals pi over 2. But because we want all radian solutions, we have to add a 2 pi times k, where k is in z. All right, let's do cosine of square root of 2 over 2. All right. X cosine is square root of 2 over 2 at pi over 4. It's also square root of 2 over 2 at 7 pi over 4. And we're going to add plus 2 pi k plus 2 pi k, where k is contained in your integers. And again, the whole time you're looking at unit circle to see where cosine is positive or equal to 2 over 2. Because f of x equals tangent of x and g of x equals cotangent of x have a period of pi and not 2 pi, we can add pi k or 180k to abbreviate an infinite number of solutions for these two functions. All right, so now we have to limit what we work with, particularly tangent and cotangent. They have a period of pi. So instead of adding 2 pi, we're only going to write pi plus pi. So let's do in class example 8. Find all the values of the variable that make the equation true. So when is tangent radical 3 over 3? All right, so we see that tangent is radical 3 over 3 at pi over 6 and 7 pi over 6. But didn't we just say that tangent has a period of 0 to pi? So only one of them would work. Only the pi over 6 would work. So our answer would be x is equal to pi over 6 plus pi k, not 2 pi, pi k, where k is contained in z. Let's do cotangent 0. When is cotangent 0? Cotangent 0 is at 90. And also, right here again, at 180, I'm sorry, at 270. But we just said that tangent and cotangent are limited from 0 to pi only. So therefore, our answer would be 90 degrees. We're using degrees and not radians because we have a theta. So my answer would be theta is equal to 90 degrees. And we have to write that k argument. Plus pi times k, where k is contained in your integers. Solving trigonometric equations. So here's where your factoring comes in handy. The work we did earlier in the section was to prepare us for solving equations that are less direct, as demonstrated in the next examples. If these were algebraic equations, we would isolate the variable. However, trigonometric equations are typically solved by isolating the trig function, not the variable in the argument. So in example 9, solve for theta, where theta is between 0 and 360, for square root of 3 tangent theta minus 1 equals 0. So if it's helpful, you've done something like this. How would you approach it? How would you do it if you had something like 3x minus 1 equals 0, and it asks you to solve for x? Would you be able to do so? Yeah, right. Even if I put square root of 3, yeah, you can still continue. So it wouldn't be different if instead of x, I write tangent theta. Your goal is still to isolate your unknown, which is tangent theta. So we want to start off by isolating tangent theta. So we want to move the constant to the right side. So we want to do minus 1, so we add 1 to both sides. And we're left with radical 3 tangent theta equals 1. We divide by square root of 3, square root of 3. We equal tangent theta is equals 1 over square root of 3 over 3. It's 1 over square root of 3. And we want to rationalize because that's how we find it in our unit circle, right? So tangent is square root of 3 over 3 at 30-degree marks. So it's here, 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 and here. But positive, it's only the ones written in black, right? Now, we said that tangent is limited. Tangent and cotangent are limited to 0 and pi. So our only answer is 30. And 210, why is it saying 210? Oh, because we want between 0 and 360. So that would be our answer. Example 10. Solve for x when x is between 0 and 2 pi for cosecant theta. Cosecant squared x minus 2 equals 0. So again, we want to start off by isolating our argument, that cosecant squared x. So we start off by moving the 2 to both sides. So plus 2 plus 2. We're left with cosecant squared equals 2. We take the square root of both sides. And we have cosecant x equals plus or minus square root of 2. So I have two arguments. One is with the plus square root of 2, one's with the minus square root of 2. So I see where cosecant holds true for those arguments. It's true for 45 degrees, 135, 225, and 315. And those would be our answers. Now notice we're not adding a plus 2 pi. k because it's telling us that our answer is only going to be found between 0 and 2 pi. If I were to say all, then I'll do the plus 360k, where k is contained in z. But that's not the case for this problem. Example 11, solve all possible degree values for theta where cosecant theta plus 2 equals 0. All right, all, right? We see that all being written. So because we see all, we know we're going to do the plus 360. We have theta, okay, where k is contained in z. So that's just a hint to keep in mind. All right, we want to solve for cosecant theta. So we want to solve for theta by subtracting 2 to both sides, and that's it. When is cosecant theta equal to -2? We use our unit circle, and that only happens at 210 and 330. So we write theta is equal to 210, and theta is equal to 330, and we add our extra part to our answer. We do that because we want all possible answers. Okay, let's see you try it one. So we want to solve for x. We want all possible radiant solutions, right? So I'm giving myself a hint. I have to add a plus 2 pi k, where k is contained in z. Let's go ahead and work this problem out. So I have 2 cosine of x plus 1 is equal to 0. I want to get cosine of x by itself. That's the goal. All right, so I have to start off by moving the 1. So I do -1, -1. And I'm left with 2 cosine of x is equal to -1. Now I have to divide by a 2 to get cosine by itself. And we're left with cosine of x is equal to -1/2. All right, so when is cosine equal to -1/2? You can take a good unit circle, or you can stop and think. All students take calculus. Our answer is going to be in quadrants 2 and 4, and we take a look in the circle. When is cosine -1/2? In quadrant 2, cosine is -1/2 at, we're using radian values, so it's -1/2 at 2 pi over 3. And it's also -1/2 in quadrant 3. Oh no, C for cosine. So this one right here, cosine's positive in quadrant 4. And it's -1/2 in quadrant 3 at, right here, at 4 pi over 3. So those are our answers. So we write x is equal to 2 pi over 3 and 4 pi over 3. But because we want all possible solutions, I have to write plus 2 pi k plus 2 pi k. We have to write when k is contained in z. When k is contained in z. Let's continue. No solution. It is possible to have a trig equation that has no solution, as shown in this next example. So we have solve for x when x is between 0 and 2 pi for 3 cosine of x minus 4 equals 0. Okay, so we want to solve for cosine of x and I have to move everything else. And we're left with cosine is equal to 4 over 3. If we take a look at a unit circle, is cosine ever 4 over 3? No, right? In a unit circle, we have numbers like 0, 1, 1/2, radical 2 over 2, radical 3 over 2, but never 4 over 3. So because that's not a value in a unit circle, we're going to say no solution. Now we could use our calculator, but as of now, we're pretending like there's no such thing as a calculator that would help us. Because cosine function can never be greater than 1, it is not possible for cosine x or cosine theta to be 4 over 3, as shown on the right. In other words, there is no solution for 3 cosine of negative 4 equals 0. The same is true for sine x and sine theta. Sine and cosine values are between negative 1 and 1. I'm sorry. So if we were to use a calculator, it would just say error. Quadratic form. Sometimes a trigonometric expression contains a function as sine x and the square of the same function, sine squared x. In this same case, the expression may fit the pattern of a quadratic expression. If so, then the trig expression we say is in quadratic form. For example, the expression sine squared x plus sine x minus 2 is quadratic in form and is possibly factorable. To factor, we can temporarily substitute a value for sine x, such as w, where w is equal to sine x, and use a factoring technique for trinomials. So here it's saying, hey, we can take the time and say, let w equal sine x. So we can replace sine x with a w and sine squared x as w squared. Now I can go ahead and factor. If we factor, we're left with this. And then I can take a w and replace it back with sine. So that way I can factor a trig function without getting too overwhelmed. So let's do in class example 13. We're being asked to just factor the expression. All right, we're going to begin and say, let w equal cosine. We're dealing with cosine, we'll write it cosine of x. So that we have 2 we're saying cosine squared would be w squared plus 5w minus 3. Okay, can we factor this? Yeah, we can. 2 times negative 3 gives me negative 6. Our middle term is positive 5, so 3 and 2 will do the trick. We'll make the 2 negative, so my 5 can be positive. So this can factor to be 2w plus 3w minus 2w minus 3. I can factor my first 2 and my last 2, so that I have w times 2w plus 3, factor negative 1, and have 2w plus 3. So this factors to be w minus 1 times 2w plus 3. Cool, that factored out. Let's just go back and change my w to cosine. Then my final answer would be cosine of x minus 1 times 2 times cosine of x plus 3. Let's move forward. If the quadratic in form expression is a binomial, then different factoring techniques may be used. All right, so everything you've ever learned in the past about factoring comes back, and it applies here into your trig course. So let's take a look at A. Tangent squared minus square root of 3 times tangent. If you're ever confused by the use of all the trig functions, you can always replace it with the w or with the x or with the v. So let's say let tangent of x equal to w. So I have a tangent squared, so that'd be w squared, and I have a tangent right there. So we can replace it to be w squared minus square root of 3 times w. Would that help you factor? Yeah, we see they have a common factor of w, so I can factor w, so we're left with w minus square root of 3. And I can go back to use the tangents like we're supposed to because we want to work with tangents. So this factors to be tangent of x times tangent of x minus square root of 3. All we did was go back and replace my w's with tangents because that's what w is equal to, tangent. All right. So again, if you're confused, you can replace it with a w or a u. So let's do u. U is equal to cosecant of x. So this would be u squared minus 4. Can we factor this? Yeah, and it gives us a hint. This is a difference of squares. So this can factor to be u minus 2 and u plus 2. Let's go back and replace u with cosecant. So our answer would be cosecant of x minus 2 and cosecant of x plus 2. All right, let's do you try it too. You've been pretty quiet, and I'm thinking maybe it's just because all making sense. But go ahead, you try it too. I'll give you 2 minutes, and then we'll go ahead and meet back and see how you're doing. All right, you have 2 minutes. Are you guys still there? Yeah, so people here. Okay. Making sure you guys are still around. Okay, screen and share my content again. All right. So I asked you to factor these. Now, I'm not sure how comfortable you're factoring. I'll upload some videos. I'll email them to you of videos that I like of how they go over factoring as review in case you feel like you need more of a review. Factoring will be very helpful. Not everything will be factorable in this section or this chapter. All right, so let's go over that first one, secant x. We're going to let secant, that's not cool. Secant x be replaced with w. So if we replace it with w, we're left with w squared minus 2w minus 8. All right, so what two numbers multiply to give us -8 and now to give us -2? 4 and 2 work, where 4 is negative. So this factors to be w minus 4 and w plus 2. All right, now we have to go back and change it to secant. So this factors to be secant of x minus 4 times secant of x plus 2. Cosine x, 4 cosine x squared minus 1. All right, let's let u equal cosine of x. And if I make the replacement, I'm left with 4 u squared minus 1. So we can notice that this is difference of squares. I have a minus and I have two terms that are perfect squares. So this factors to be u, 2u plus 1 and 2u minus 1. So we have 2 cosine of x plus 1 and 2 cosine of x minus 1. Lastly, c. Now you don't have to do a substitution each time. As you work with these, hopefully you feel more comfortable. So we see that we have a sine squared x and a sine. So we can factor a sine x. So that we are left with sine of x times 2 sine of x minus 1. But again, you never have to skip that substitution. If you feel like that's something you need to do, you can always make a substitution argument for whatever you're working with, like we did for A and B.
You walk
All
me
right.
through that last one again. See?
See? Yeah. So we can do substitution. I just chose like, hey, we don't have to each time. So I said, you notice that we have a sine squared and a sine, so we can factor out a sine. So that we have sine of x. What are we left with? Sine squared divided by sine, we're just left with sine. So we have 2 sine of x minus sine of x divided by sine, we have 1. Now again, you don't have to do it that way. You could always say, hey, let b equal sine of x. If we do that, we're left with 2b squared minus b. Okay, now I can easily see I can factor out a b. So I can factor a b and have 2b minus 1. All right, we said that b was sine. We're left with sine of x, 2 times sine of x minus 1. So you can always do a substitution. It takes practice before you get comfortable with not having to do a substitution, but that just comes with practice. You don't ever have to skip using a substitution. I highly encourage you to do a substitution. All right, why are we factoring? Why are we spending so much time factoring? Well, the reason for this is because we have the zero property rule, and that makes things very easier for us when it's factorable. If a trig equation contains an expression that is in quadratic form, then one side of the equation should be 0. The other side is the quadratic, and the equation can be solved by either factoring the quadratic or by using the quadratic formula. If the quadratic can be factored, we can use the zero product principle, and that's so helpful in math. So this is saying if I have 2 things that are being multiplied and they're equal to 0, then I can set my first factor equal to 0 or my last factor equal to 0. If one of them is 0, it makes our whole answer 0. The zero product principle says this: if the product of 2 or more factors is 0, then one of the factors is 0. And we must consider all possibilities to identify the solution. All right, let's do example 15. Now we can put everything we worked with together when it comes in terms of factoring. Example 15. Solve for x when x is between 0 and 2 pi for the equation 2 cosine squared x minus cosine x minus 0. All right, now it doesn't work for us. Let's read through the example. The left side is in quadratic form. We factor the left side of the equation and set each factor equal to 0. So we're going to factor, and this is what it factors to. Now, according to our zero product property, we can take each factor and set it to 0. So we have cosine of x equals 0, and the other factor, 2 cosine of x minus 1 equals 0. We solve for x separately on each one. All right, so when it's cosine 0, cosine is 0 at pi over 2 and 3 pi over 2. That's part of our answer. Now, our second part, we want to solve for 2 cosine x minus 1 equals 0. So we want to go ahead and we want to add 1 to both sides, divide by 2. And we're left with cosine of x equals 1/2. When is cosine of x 1/2? And we see that it's 1/2 at pi over 3 and 5 pi over 3. So what our answer is all of these put together. We want to write them as one answer. So we put all of our solutions together and we get that x is equal to pi over 2, 3 pi over 2, pi over 3, and 5 pi over 3. All right, factor the left side. example 6, solve for x for the equation sine squared x plus 3 sine x equals 0. We want to factor. Since we see we have a quadratic, we should try factoring. So if you ever don't like the way it's done in the example, you can do it the way we did with the substitutions. So we see a sine x, so we're going to let w equal sine of x. If we do that, we can rewrite this to be w squared plus 3w equals 0. And we can try to factor from there, right? If we factor, we see from each term I can factor out a w. And I'm left with w times w plus 3. Cool. I can solve each one for 0. Let's solve each one for 0. We can solve each one for 0 right here. So I have w is equal to 0 and w plus 3 is equal to 0. Let's work them out. So this one, the first one is done. W is equal to 0. Let's change w to sine. So I have sine of x is equal to 0. When is sine 0? For the next one, I can go ahead and solve for w. Minus 3 minus 3. W is equal to negative 3. All right, we said w is sine. Sine of x equals negative 3. So you can always work through it as a substitution. All right, so we're here. Sine of x equals 0. Sine of 0 at 0 and pi. Now we got sine is equal to negative 3. You said that they don't go past 1. So that's a false solution. So sometimes you can have solutions that aren't true. So this is a false solution, an extraneous solution. So our only answer is 0 and pi. I don't know why this picture's here. I don't think that should have been there. I think that's just the picture from the example above. Now let's take a look at example 17. Solve theta when theta is between 0 and 360 for secant squared theta plus secant theta minus 2 equals 0. All right, just as we said before, you can go ahead and change it to w's. And it does that right here on the side, where you can factor and change it to w's. And we're left with w plus 2 and w minus 1. All right, let's change our w's to secant. So we're left with secant theta plus 2 and secant theta minus 1 equals 0. So we do one more step. We go ahead and move our numbers, minus 2, minus 2. We're left with secant theta equals negative 2. When is secant negative 2? All right, well, we see that secant is 2 at 60 degrees, and therefore it's negative in quadrants 2 and 3. So my answer is 120 and 240. Next one, when is secant 1? And we see that secant is 1 at 0. So our answer is only 0, because remember, we're not including 360. So we put our answers together, we get theta is equal to 0, 120, and 240. All right, let's do you try it 3. I'll have you actually try it. I'll give you about 3 minutes because I know these are different and they're kind of weird. Now, as you work through this one, you work with a quadratic. Whenever you work with a quadratic, you first have to set it equal to 0. So let's do that first part. So let's add 5 to both sides, add 5. So we're left with 2 sine squared of x plus 11 sine of x plus 5 is equal to 0. Okay, now we can go ahead and factor. So go ahead and solve for x, given the equation 2 sine squared x plus 11x plus 5 equals 0. I'll give you 2 minutes. Okay, let's see how far you got. Now I know this is different, so be very patient with yourself and give yourself time to work through these problems. Now this is a problem where for sure I would do some substitution. So we have sine of x and sine of x squared. So let's say sine of x is equal to w, since w has turned into our default letter. Let's rewrite it. We have 2w squared plus 11w plus 5 is equal to 0. Okay, I want to solve, but I see I have a quadratic. And at this moment, we're completely avoiding quadratic formula. We're hoping factoring works. Okay, so I want to multiply my first and last number. 2 times 5 give me 10, and my middle number is 11. So what two numbers multiply to give me 10, but add to give me 11? That's 10 and 1, right? 10 times 1 gives me 10. 10 plus 1 gives me 11. So we're going to replace our middle number with 10 and 1. So that we now have 2w squared plus 10w plus 1w plus 5 is equal to 0. Now I can group my first two and I can group my last two. If I group my first two, that would factor to be, well, I can factor a w, and they're both even, a 2. So we're left with w plus 5. On my last two problems, I see that it already looks like what I have in the parentheses. Plus, there's something else to factor, so I can just draw and write a place value of 1. I can factor 1, which doesn't change anything. It just helps me keep track of our factoring. So my answer for factoring, I'm left with 2w plus 1 and w plus 5 is equal to 0. All right, now I can set each one separately equal to 0. So that we have 2w plus 1 is equal to 0. And we also have w plus 5 is equal to 0. Now you have options. You can now change it back to your substitution. We said w is sine. Or you can wait till you completely solve for w to replace it. Your call when you change it back. I'm going to change it back now. So I have 2 sine of x plus 1 is equal to 0. And sine of x plus 5 is equal to 0. Okay, let's solve for sine. Let's get sine by itself. So I do plus minus 1. Minus 1, minus 1. I'm left with 2 sine of x is equal to negative 1. Divide by 2, divide by 2. Sine of x is equal to negative 1/2. That's my first one. Okay, so now we have to look at unit circle. Have unit circle paper out. Look at it. When is sine negative 1/2? And for sine and cosine, you don't really have to think, hey, where is it positive or it's negative, because that one's x and y. You can just look at your coordinate points. And you see that your y's are negative in quadrants 2 and 4. We see a negative 1/2 for the y at 210 degrees and 330 degrees. But I already made a mistake because we have x and it's telling us to use radians. So we have to make sure to write as radians. We want x is equal, instead of 210, I want 7 pi over 6. And instead of 330, I want 11 pi over 6. And I purposely wrote that above because if you're using a unit circle, you can easily go back between radians and degrees. It's written right next to it. All right, almost done. Let's take a look at the next one. We want to solve for sine x plus 5 equals 0. So we subtract 5, we subtract 5. Sine of x is equal to negative 5, and that's undefined. Remember, sine and cosine only have an amplitude of 1. We can go to 2 only when we're working with cosecant and secant. All right, so our answers are, we have them down. X is equal to 7 pi over 6 and 11 pi over 6. Now, before we take off, I know you're probably super tired. You've been on a Zoom conference for 2 hours already, but I always like to do some problems with you before I call it a day, just to make sure we're in good shape. So before we leave, how about we do, I want to do some ugly ones with you. Okay, let's do 13 and 15. Let's do those two before we call it a day. And after that, I'll answer homework questions. Okay, so do 13 and 15. I'll give you 5 minutes. I'll stop you at 4:05. So go ahead and give 13 and 15 a try. All right, it's been 5 minutes. Let's go ahead and see what 13 and 15, what the answers to those are. So let's work them all together. Now, something that's really important in every math problem is to read your question. Now, it's asking us to solve for all possible radian values. So just because I'm a super forgetful person, I'm going to write above that, hey, don't forget to do that plus 2 pi k, where k is contained in z, because I will forget. Okay, so let's go ahead and solve that secant squared problem. So I have secant squared x plus 2 secant x equals 0. Now, that looks unfamiliar, so why don't I change that secant to a w? So I have w is going to equal to secant of x. Now, if I rewrite it, I'm left with w squared plus 2w equals 0. All right, now I can say I can factor a w, and I'm left with w times w plus 2 is equal to 0. Let's change my w to secant. And because of my power, what's it called, your product rule, I know I can set each product equal to 0. So I have w is equal to 0, which is secant of x is equal to 0, and w plus 2 is equal to 0. If I replace w with secant, like we said we would use, I have secant of x plus 2 is equal to 0. All right, let's solve for secant. The first one is solved, and I want to see where secant is equal to 0. And we see that secant is never 0, right? Secant, our options for secant are 1, 2 square root of 3 over 3, square root of 2, 2, and undefined. We never have a 0. So this one is a undefined, no solution. All right, let's go ahead and solve the next one. So I want to go ahead and move 2 minus 2 minus 2. Secant of x is equal to -2. All right, secant is 2 at 60 degrees. So I'm writing a note. I know it's 2 at 60 degrees. So I'm going to draw a little unit circle just for myself. And I want -2. I know it's positive at, well, all students take calculus. I know it's positive at all and at cosine. So negative would be quadrant 2 and quadrant 3. So the 60 mark in quadrant 2 is 120 degrees, and the 60 mark in quadrant 3 is at 240 degrees. But our question wants radians, so we'll write it as radians. Instead of 120, I'll write 2 pi over 3. And instead of 240, I'll write 4 pi over 3. So my answer is x is equal to 2 pi over 3 and 4 pi over 3. My final answer is x is equal to 2 pi over 3 plus 2 pi k and 4 pi over 3 plus 2 pi k. And we're going to say when k, or where k is contained in your integers. C. So that's number 13. I'm going to screenshot it just so you have it handy for you to have. Okay, let's go on to 15. Solve for all possible degree values with theta of theta. So we want all values. So I know at the end I have to write plus 2, not 2, 360k where k is contained in your integers. Okay, let's solve 15. This looks unfamiliar. Mainly all those cotangents look weird, so let's go ahead and change cotangent to a w. So I have w is equal to cotangent theta. Let's replace it so that we have w squared plus 2w plus 1 is equal to 0. All right, that's something I can work with. So what numbers multiply to give me, well, I have a 1. 1 times 1 is 1, and middle number is 2. What numbers multiply to give you 1 and add to give you 2? 1 and 1. All right, because my leading coefficient's a 1, I already have my answer. It's 1 and 1. So w plus 1 times w plus 1 is equal to 0. Let's go ahead and rewrite both separately so I can go ahead and solve. So I have w plus 1 is equal to 0. And we said w is cotangent. So I have cotangent theta plus 1 is equal to 0. We solve for cotangent, minus 1, minus 1. We have cotangent of theta is equal to negative 1. And we see that cotangent is 1 at 45 degrees. So I'm going to draw my circle. At 45 degrees, we want negative. All students take calculus. So cotangent is positive in the first and third, we want negative. So we're going to work with second and fourth. And cotangent is 1 at the 45 tick mark. So right here at the 45. So we'll have 135 degrees and 315. So my answer for the first one, theta is 135 and 315. But we're not done. That was that first one right here. You have to do the other one. W plus 1 is equal to 0. Let's replace W with cotangent. Cotangent of theta plus 1 is equal to 0. We subtract 1 to both sides. We're left with cotangent of theta is equal to, did I write it wrong? No, it was the same thing twice. I didn't have to do all this work. It's the same thing. So my answer is, my final answer, we want to write theta is equal to 135 plus 360k, and theta is equal to 315 plus 360k when k is contained in your integers. Whoa. All right, so that's the answer 15, in case you want to take the time to screenshot it, just so you have it handy. Now, before I move forward, that's it for today's lecture. I'd like to reserve the last 15 minutes in case you had homework questions from any of chapter 4 problems. So do you have questions from chapter 4? I'm sorry, chapter 5?
I had a quiz question.
Sure.
I have one more quiz to do, and it's I think it's section 5.2.
Okay.
And I cannot access it because it says that it's part of an unpublished module, and I don't see a module for week 10. So I think that's probably what the issue is.
Okay. So week 10, I never made it visible. So you should be able to do it now. Thank you for letting me know.
Yeah, no problem.
So it has this weird thing. I wish I could show you my canvas. Maybe I can show you my canvas. So I can add things to the week within a module, but within each module, I have to publish it. So what it was is, so you can see my screen. I didn't have that first green circle, I didn't have it green. So even though I had a week 10 homepage, and even though I had a 5.2 quiz written and available, because I put them under week 10, and that wasn't in blue, that wasn't green until just now. You weren't able to access it. So you should now be able to access it. I'm sorry.
Got it. Thank you.
Yeah. Any homework questions from 5.4 or 5.1, 5.2, 5.3?
I have 3 questions from 5.4.
Yeah, what are they?
5, 11, and 17.
Okay, let's take a look at those. Let me jump back to chapter 5, 5.4. 5, 11, 17. Let's take a look at 5. Ooh, it's the ugly one. All right. So these are fun. They really make you challenge everything you know thus far. All right. So we're working in quadrant 4. Let me just draw my quadrant 4 real quick. All right. My quadrant 4 triangle. And tangent of A is equal to -2/3. All right. I know tangent. Sine is y over r, so tangent is y over x. Okay, so we're saying that my y is negative. Y is -2. That makes sense because my y's are on the negative side. And my x is 3. That makes sense because my x is positive. My y's are negative. Okay, so far we have that x is 3 and y is -2. Right, we get that from above. Okay, now we have to find r. We can find r using x squared plus y squared. So x squared would be 3 squared plus y squared -2 squared is equal to r squared. So that'd be 9 plus 4 is equal to r squared. 9 plus 4 is 13 is equal to r squared. We take the square root. Plus or minus, we want positive because r is always positive. It's the hypotenuse. So it's square root of 13. So we have now found that r is square root of 13. All right, we know cosine is x over r and sine is y over r. Let's make a replacement now that I know x, y, and r. So cosine is x over r, x is 3, and r is square root of 13. Sine is y over r, y is -2, and r is square root of 13. Now we could rationalize, but there's no point because I have to work with my formulas next. All right, so let's go ahead and use our formulas. So take out your beginning of your section, have your formulas handy. Let me pull out my formulas. All right, so sine squared can only come from one of them because we only have a double angle for sine. So that would be 2 sine of A times cosine of A, right? And we have sine of A and we have cosine of A. Let's make that replacement so that we have 2 times sine of A is -2 over square root of 13, and cosine is 3 over square root of 13. We can write that 2 as 2 over 1, and let's multiply across. 2 times 2 times 3 is -12. And square root of 13 times square root of 13 gives us 13. And that's our answer. Now cosine of 2a, we have 3 different options for a cosine double angle identity. Pick whichever one you'd like. I'll use cosine squared A minus sine squared A. All right, I know what cosine A is and I know what sine is. Let's replace it with a square. So cosine of A is 3 over square root of 13 squared minus sine squared A. Sine is what? Sine is negative 2 over square root of 13 squared. So 3 squared, 3 times 3 is 9. 13, square root of 13 squared is just 13 minus negative 2 times negative 2 is positive 4. Square root of 13 squared is 13. 9 minus 4 is 5 over 13. 5 over 13. That's the answer. So that's number 5. All right, so if you'd like to take a screenshot of it, so you don't have to wait for the video or look through the video. Let's take a look at number 11. Number 11, you want to use a double angle identity to simplify each. Okay, so I see cosine squared minus sine squared of an angle. Let's say this is an A. Let's rewrite it. I can't add it. Well, first of all, you should know you have to rewrite it because you don't have 15 in unit circle. So how can you find that value squared if you don't know what that represents? You do not know what 15 is. So we see that this is the same thing as cosine squared A minus sine squared A. Do we have a formula for that? Yeah, we do, right? And that is a double angle for cosine. So the same thing as cosine of 2A. So this is my A. My A is 15. Let's replace it. So this is going to equal cosine of 2 times 15. 2 times 15 is 30. So cosine at 30 is 1/2. Is it? Did I guess right? No. Cosine at 30 is radical 3 over 2. So my answer is radical 3 over 2. Did you understand 11? I know this was something that was giving us trouble on Tuesday's lecture.
Yeah. Thank you.
Okay,
Mhm.
you're welcome. All right, so let's move on to number 17. All right, so we want to rewrite it. First of all, a big hint that you have to rewrite it is if you look at unit circle, nowhere do we have a 3 pi over 8, right? We don't even have one with a denominator of 8. So we know we have to use our identities. Luckily, we only have one formula for tangent. Our tangent formula is tangent of 2A is equal to, and that's what we have. We have what it's equal to. 2 tangent of A divided by 1 minus tangent squared. So what we have here is what we have here. Now what I want to do is I want to seal the value of A. So let's make A equal 3 pi over 8. And let's replace it here with this A. So that I have tangent of 2 times 3 pi over 8. Let's multiply across. We can write it as over 1. So we're left with tangent of 6 pi over 8. And that reduces, right? That simplifies to be, I have a common factor of 2. 6 divided by 2 is 3. 8 divided by 2 is 4. So we're left with 3 pi over 4. 3 pi over 4 is 135 degrees. So we want to find tangent at 135 degrees. That would be -1. So our answer is -1. If the radians throw you off, you can always write it as degrees. What is tangent? You find 3 pi over 4, that's 135 degrees. What's tangent at 135 degrees? Think of it that way. I know radians can sometimes make, it can kind of confuse us if we're not used to seeing those values. All right, so that was 5, 11, and 17 from section 5.4. Are there any other homework questions from chapter 5?
Yeah. Let's just go to 23, I guess.
23?
Yeah.
All right. Add and subtract to create a double angle identity. Okay, so we have 2 cosine squared of 3 pi over 4. All right, so I see that I have a 2 and a cosine squared. So this almost looks like, big almost, it almost looks like one of our cosine double angle formulas. And it says cosine of 2a is equal to 2 cosine squared a minus 1, right? And what I'm saying it almost looks like that is if we let a equal that 3 pi over 8, then it almost looks the same. I have 2 cosine squared of an a, 2 cosine squared, but that's where it stops. I need this plus 1. Do I have that plus 1? We don't. That's what we need to finish it so it can look like that. Okay, so let's include that minus 1. So let's write minus 1 so it can look the same. But if I take away $1, you're missing $1. It's not the same thing. You're $1 short. So I have to compensate it by adding a 1. Because if I take away $1 but give you back $1, nothing changed, right? So we have done that. So let's rewrite it, just like we have above. We have 2 cosine squared of 3 pi over 8 minus 1 plus 1. So what we did was we wrote a minus 1 and a plus 1. We didn't change the value of it because we didn't add anything. Plus 1 minus 1. Plus 1 minus 1 is, you're not changing it, you're just writing things. We write this so that it can look like what we have above. 2 cosine squared of a number minus 1. Cool. Let's focus on just this part. Now, according to our equation, this is the same as cosine of 2 times their value, 2 times 3 pi over 8. So let's go ahead and do that. So this is cosine. This is cosine of 2 times 3 pi over 8. All right, let's go ahead and evaluate. Let's multiply. Cosine. All right, my 2 and my 8 divide to make. So 2 divided by 2 is 1, 8 divided by 2 is 4. So that is now 3 pi over 4. All right, cosine of 3 pi over 4 is negative square root 2 over 2. Cool, just about done. Just don't forget about that plus 1 that you wrote. So then you write plus 1. So now you have to do a bit more work. Let me continue over here. I'm sorry for all my arrows. So now I'm left with negative square root of 2 over 2 plus 1. I need a common denominator. So negative square root of 2 over 2 plus 2 over 2. I'm left with negative square root of 2 plus 2 over 2. And that's our answer. We don't like to start with a negative, so let's switch our terms. So that we have 2 minus square root of 2 over 2. That would be our answer.
See, Bob Pryor's getting something else entirely.
Yeah, he has errors.
Okay, see, that was killing me. I'm sitting here doing this math and not getting what he's got written as the answer. So he has 1 minus square root of 2 over 2 as his answer.
Nah, that's not right. Oh, you're saying he has 1 minus square root of 2 over 2?
Yeah, that's the answer that he has for 23.
That's okay, because remember, always draw a heart to help remember this 2 is dividing this 2, and it's dividing this 2. So you can divide 2 over 2, that'll give you 1, and square root of 2 over 2, that you can't simplify any further. So that stays at square root of 2 over 2. So that's okay. They're both the same answer.
Got it.
I know it's silly that I'm always drawing a heart, but it's just to help remember that 2 is dividing each term separately, even though we only write it once.
Professor, just to clarify, so if you have a radian that's not on the unit circle and you want to get a value that's on the unit circle, you use the left side of the equation or of the formula.
Yeah, that's exactly the whole purpose of these formulas in chapter 5, is we're saying there are ways to go around finding the exact value of a cosine of a degree or sine of a degree without having to refer to a calculator. Now what we're writing is the exact formula. So yes, to answer your question, yes, if it's a number that's not a unit circle, that should be a big indicator that you need to use a formula.
Okay. Thank you so much for your help.
You're welcome. I'm here to help. All right. Are there any other questions for chapter 5?
Number 27, please.
27?
Yeah.
Okay. Let's take a look at 27. Ooh, these proving ones. These are always so tricky. Verify each identity. Manipulate one side only. Okay. So I see my right-hand side and my left-hand side. And you have to make a choice of which you're going to start working with. Now, they kind of both look equally complex, but we see here we have a sine 2 theta or sine 2x. So we know we can rewrite that and expand that more. So let's go ahead and work with our right-hand side because there seems more work that can be done. Okay, so let's go ahead and do that. We're going to choose to work with our left-hand side. Okay, so let's replace this first part, that's sine 2x. So I'm going to write down my formula on the side just so I remember when I look back at my notes. And I'm like, where did that change come from? So sine of 2a is that formula. Sine of 2a is equal to 2 sine a cosine a. 2 sine a times cosine a. So let's make the replacement. But instead of a, I have cosine. All right. So I have 1 minus 2 cosine or sine 2 sine of x times cosine of x. All right, and that's all I can do so far with sine and cosine. All right, so now I'm kind of stuck. I don't know what I can do. So why don't it's written in terms of sine and cosine. So that step is checked from our list. And we see that we want to get sine of x minus cosine of x squared. Why don't what can we try to do? Multiplied. I'm kind of stumped with this one. Well, why don't we try working with our left-hand side? Right-hand side didn't work. Let's go with left-hand side.
Okay.
Okay. So in our right-hand side, we have sine of x minus cosine of x squared. If we expand it, if we FOIL, this would be the same thing as sine of x minus cosine of x times sine of x minus cosine of x. And I can multiply everything out. This multiplies to be sine squared of x minus 2 cosine x times sine x plus cosine squared x. That's what it multiplies out to be. Right? You can do sine times sine gives you sine squared. Sine times cosine gives you minus sine times cosine. Negative cosine times sine x is another negative sine cosine x. And cosine, negative cosine times negative cosine gives you cosine squared x. Okay, now I want it to look like on the right, 1 minus sine of 2x. Now, I'm still going to use that formula where it's telling me that sine of 2a is 2 sine of a cosine of a. I have that. Don't we have that? We have this here. 2 cosine of x minus sine of x. We know that that is sine 2a. So let's rewrite what we have so far. We have sine squared x minus sine of 2a plus cosine squared x. Okay, now we're just missing that 1. How can I get 1 from sine squared and cosine squared? Okay, we can use our Pythagorean identities.
Is that actually sine 2a? Because sine 2a, is it not 2 sine times cosine of a? Not rather than being 2 cosine times sine?
Oh, multiplication doesn't have order. Just like 2 times 3 is the same thing as 3 times 2. So I can have sine times cosine or cosine times sine.
Gotcha.
That's a very, very good question. Thank you for asking that. All right, so lastly, we're almost done. I have my sine and my cosine to get rid of. So I know by our Pythagorean identities that sine squared x plus cosine squared x equals 1. So we have sine squared x plus cosine squared x minus 2 sine of a. I know these add up to 1 or make up 1. So I now have 1 minus 2 sine of a. So we have now proved that 1 minus 2 sine of a is equal to 1 minus 2 sine of a. So this one, I like this one so much because it shows you how sometimes, even if it's your teacher, sometimes we might start thinking one way and start working through it, but it doesn't always work out. So for me, I thought, hey, the right-hand side is the side I want to work with. But once I started, I got stuck. So maybe it wasn't the best choice. So then I stopped and I started working on my left-hand side. And I saw from there, I was able to come up with something so that I can show that the left-hand side and the right-hand side are equal. But notice, I never added to both sides. I never subtracted or multiplied to both sides. Each side was completely separated from the other.
Professor, how did you get, so you see the first blue part, how did you get to that?
Yeah. All right, so I'm going to do this work on the side. We have sine of x minus cosine of x times sine of x minus cosine of x. Now, I'm going to remind you of your formula from algebra. You have A plus B squared is the same thing as A squared plus 2 times A times B plus B squared. Right? So if you let A equal sine of X, you let B equal cosine of X, you can go through the process and get your final answer without having to FOIL. So I did this without FOILing using the formula. But sometimes we forget. So let's multiply it out. So sine of X times sine of X, that gives me sine squared of X. Sine of X times negative cosine of X, we get minus sine of X cosine of X. Cosine of X times sine of X, we have minus cosine of X times sine of X. And lastly, negative cosine of X times negative cosine of X, we have positive cosine squared of X. All right, let's go ahead and clean this up. So I only have one sine squared of X. So I have sine squared of X. Now I have minus sine of X cosine of X and a minus cosine of X sine of X. They're like terms because they both have a sine and a cosine of X that are being multiplied. Remember, in multiplication, order doesn't matter. So I always say 3 times 2 is the same thing as 2 times 3. So cosine of X and sine of X is the same thing as sine of X times cosine of X. So I have a minus 1 and a minus 1. I get negative 2 sine of X cosine of X. And lastly, I'm left with that cosine squared X. So plus cosine squared X. And that's what we have here.
Oh, okay.
So the final answer was it 1 minus 2 sine A?
Yeah,
Is that
we worked with, yeah, I'm sorry.
Is that the same as 1 minus sine 2x?
Oh, I switched between X's and A halfway. It's X's, not A's.
But is sine, we'll say sine 2a, is that the same as 2 sine A then?
Yeah, I just messed up my variables, but it's the argument and our work in between is still same. Just change your X's to A's.
Well,
I mean,
okay. I mean, the x or the a aside, does the placement of that 2, as in the x is being multiplied by 2 rather than the sine, does that matter at all? If you look at what, like for example, 27, what the equation is.
oh, I just got messed up on my writing halfway. So you see how here I have sine 2 of A?
Mhm.
Sine 2 of A is very different from 2 sine A. So I made a mistake there in the writing. I just got scrambled up with my writing. So that is sine 2A, sine 2A, sine 2A. Yeah, thank you for catching that. That's very, very different. You're very right. They're not the same thing.
Mhm.
Okay. Any other homework questions from chapter 5?
Number 3.
Number 3?
Yeah, please.
Yeah. All right, I'll do this as the last one I'll do, and you can try the rest on your own. I'll give you the weekend to try. Oh, we already did number 3. We did that one in class yesterday.
Oh, okay.
Oh, so you have that one done. You want to take a screenshot of it, or you can wait till I post it on YouTube. All right, so make it a point to work on your homework for what we've done so far. I've been assigning all odds, so even for section 6.1, your homework is all odds as well. Okay, that's it for today. I'll go ahead and email you some stuff. I want to email you a cheat sheet with all of your formulas, and I also have some quizzes to post. So I'll be working on that over the weekend.
Okay.
Right.
Thank you.
Okay.
Thank you. Thank you so much for
you.
sitting through this. Thank you. Thank you. Thank you for sitting through this long lecture. But I mean, we signed up for 6 units, so we're still getting out early. We should be getting out at 5:20, right? Right.
Yeah.
Yeah.
Bye.
Bye. Have a nice weekend.
You too.
Very
All
briefly,
right, I'm gonna go ahead.
I
Yeah.
I stepped away for just a moment. The homework was it all odds again?
Yep.
Got you.
All
Thank you.
odds. So I'll answer that question for Kevin on 6.1. It's all odds. All right. Well, thank you so much. I'll see you on Tuesday.
Bye bye.
Bye bye.